Another example of a dE that can be solved by simple substitution is the dE y squared sine x dx plus 4 minus 5y cosine x dy. As you can see in this dE, we can see that the presence of both sine x and cosine x here, or the presence of cosine x and sine x dx, tells us that we can make a substitution here because if we let cosine x be a new variable, its differential sine x dx is also here. So we can let v be equal to cosine x. And it mustn't be the other way around because if we let v or u be equal to sine x, then its differential is cosine x dx, and we have here cosine x dy. So we have to be careful of that before deciding which of these two trigonometric functions here we are going to replace with a new variable. So if we let v be equal to cosine x, then its differential dv is equal to the negative of sine x dx. And so we can just simply replace cosine x here with v and sine x dx here with negative dv. So v here is cosine x. So we have cosine x here, and our dv is negative sine x dx. So substituting, the first term would now be negative y squared dv plus the quantity of 4 minus 5yv, that's cosine x is v, dy. And what we have here equals 0. So what we have here are still two variables, y and v, and then we proceed by solving the given equation now as either separable or exact or linear or Bernoulli. So let's try to see. So if we divide both sides by y squared dy, then we can have dv over dy, that's negative, so plus 4 minus 5yv over the negative y squared equals 0. So dv dy minus 4 over y squared minus, or that's plus, 5v over y equals 0. And so we can see that v here is our, we can express this as an either linear or Bernoulli. So rearranging dv dy plus 5y, 5 over yv equals 4 over y squared. So it follows the pattern of dv dy plus p of y v equals q of y, and therefore it is a linear dE. And so for the linear dE, we recall that we are only to identify which one is our p of y, which is our p of y, and which is our q of y. So now our given dE, our p of y is 5 over y, that's this one, that's our p of y, that's p of y, and our q of y is 4 over y squared. So next step is to determine our integrating factor. So the integrating factor, v, is equal to e to the power of the integral of p of y dy. So that's e to the power of 5 over y dy, or that would be e to the power of 5 ln y. And so therefore v is equal to y raised to the power of 5. And so for our general solution, For the general solution, our formula okay, so let's just use another variable for our integrating factor because we have used this twice. So let's say our integrating factor is u. So our general solution is u v equals the integral of u q of y dy plus c. And our integrating factor u is y to the power of 5 v equals the integral of y to the power of 5 times our q of y is 4 over y squared dy plus c. So vy raised to the power of 5 is equal to 4 integral of y cubed dy plus c. And so integrating, we have y to the power of 4 plus c. And our v on the left side is equal to cosine x. So substituting, that's y to the power of 5 cosine x. Or that would be y to the power of 4. That's y cosine x minus 1 equals c. And that's our general solution of our differential equation.